Hello everyone, and welcome back to NL 582, Modeling and Control of Electric Machines and Drives. In our last lectures, we start talking about the construction of synchronous machines. And we just said, like any other kind of a machine, this machine has two members, the stationary member, the stator, and the rotation or the rotating member, which is the rotor, okay? And we said before that one of those two members will be carrying the main magnetic field sources, which is either a permanent magnet or a coil connected to a voltage source. So they can act like an electromagnet to produce the magnetic field. And the member holding these sources of the main magnetic field, we call it the field member. In synchronous machine here, it is the rotor, okay? And the other member the member where the electrical part of the energy conversion happens, and this is we call the armature, where you have your induced voltage in, and this is for this kind of a machine the stator, okay? And we talked that the rotor of the synchronous machine can take two shapes. The first one on the left is the salient pole, and from its name, because it has saliency, that means it's not uniform cylindrical shape, but rather it has salient. So, and the other one is the cylindrical type on the right, like this. And both of them can hold the field winding, which can be just excited from a DC source from outside to just apply this DC voltage to the winding to produce the magnetic field you want. And because they are just supplied from DC source from by means of brushes connected to slip rings, not commutator like DC machines, because we don't want to make anything to the input voltage. We just want it to remain DC because we want the north and south poles generated from this magnet be just the same polarity all the time and the same magnitude, obviously, like we said last time, okay? And we talked so long about the pros and cons of each type of those rotors and when to use each and every one of them. Typically, the salient pole used with low speed applications and the cylindrical one used with high speed applications. That's why it's called turbo generators. The synchronous generator with cylindrical type rotor we call turbo generators. It can be used with high speed because it's more mechanically rigid and produce less noise and torque ripples compared to the salient pole. But you know that the salient pole is much simple to manufacture, and it's simple though it will be cheaper and more simple to manufacture. So everything has pros and cons, and you just decide depending on the application. And the stator, which is the armature, like you see here, holds the stator core, and it holds the armature winding, which for this kind of machine we're using for supplying electricity to the public grid, which is all in three-phase. So our winding will be also in three-phase, and that's making sense. Okay, so you have identical three-phase winding, but have a 120 degrees phase difference in space. Like you see, just using this, you can generate voltages like this. So we just had time to illustrate how the voltage is being generated from that kind of machine. So the rotor holds the magnetic field source, which is basically north and south pole. For this very simple illustration, we just use two-pole machine, just one north pole and one south pole, and just figured out how if we just apply an external source to rotate this rotor forcefully inside the stator, so the magnetic field coming from it will just cut the winding in the stator, and this will produce induced voltage in it. Okay, and we just derived from each position of this rotor rotation inside the coils here that it will produce an AC voltage induced in the winding, in the phase, each phase of them. And because these phases are spread around the circumference of the stator 120 degrees apart, the induced voltage will be typical sine waves. Each one of them will have a sine wave with the same magnitude, but they will all have 120 degrees phase also between those induced voltages. Okay, so we will have three-phase output like that, and that's what we need from this kind of a generator, because it will be just connected to the grid directly. Okay, and we want the voltage that go into the grid to be the voltage we typically use in the grid, which is balanced three-phase sinusoidal voltage and three-phase, that means it have the same magnitude, all the phases have the same magnitude, but have 120 degrees phase difference between each one and the next one, okay? Just like what you see in here, okay guys? And we started trying to quantify the induced voltage like usual, okay? I will be just writing those again. But so like you seen here from the last time, okay, that is the induced voltage per conductor, like what we just used to do, equals BLV, the flux density, times the length of the conductor times the linear speed, sine omega mt, because now that's a sinusoidal wave. It's not just constant value of like the DC machine, because DC machine obviously it's a DC value, but here it's not DC value like we see. It's just sinusoidal value like we just derived from this theory of operation of the machine here, okay guys? So it's this drawing is like the cosine wave, like I said last time, but basically it just depends when you're starting, okay? So I choose to be starting from this position where the North Pole is facing here, A, but if I started to start from this position, position 2, which is, we said like position 2, like that's no magnetic field, is basically cutting the winding, and that's 0 voltage here. So if I started to start from this position, this sinusoidal wave will be starting from 0, not from maximum like that. So you know that the cosine wave and the sine wave, they are just typically the same, they are just phase shifted a little bit by 90 degrees. So it's the same idea, it just depends on when are you starting, okay? So it's sinusoidal wave like you're saying here, so it's BLV sine omega mt, and the omega mt the mechanical speed, okay? Mechanical speed of rotation. Why I'm saying that? Because I will be just going to modify this in a little bit. So for this, it is BLV sine omega mt, E turn would be like that, and so I'm saying 2 BLV because E turn, the turn has 2 conductors, so it's basically doubling this value, so it's 2 BLV sine omega mt, and taking V by its rotational form omega mr. Omega m is the mechanical rotational speed in radian per second, okay? So to keep in mind, that is the mechanical speed, and that is because we have 2 poles. For this case, we are just trying to derive, like I said, we just have 2 poles, North Pole and South Pole, okay? Why again I'm saying that? Because it's not typically the mechanical speed, because you're talking about induced voltage, okay? That's a voltage, that's an electrical quantity, the electric voltage, okay, induced, which is E here. So it's not typically just making in terms of the mechanical speed, because the mechanical speed means it's a mechanical quantity, and it's not talking about this. Okay, I'll be saying this in a minute again. So, and I kept deriving this last time. So the same basic idea like I said last time, it is just induced voltage in synchronous machine. Okay, so like I said, E per one conductor will be equaling BLV sine omega t, but I will say now omega E, which is omega electrical, okay? Because that should be like this. But that is the whole point, to keep that in mind. It is just omega E equals P over 2 times omega m. That's a very important thing to keep in mind. The omega E is the electric speed, and the omega m is the mechanical speed. They're just related together by this relation, multiplied by P over 2, and you know P is the number of poles. That's why in the last lecture when I said that's sine omega mt, because if you just use 2 poles, omega E will equal omega m, because basically P will be equal 2, so 2 over 2 will be 1. So that means omega E equals omega m. So the general form for the induced voltage here in terms of omega E, not omega m, okay? But if you just have 2 poles, you can use omega m, because you know it will be just equal, okay guys? So the conductor induced voltage is BLV sine omega ET, like we just said now, okay? and we can just find the E turn to be just 2 of the E conductors, because each turn has 2 conductors, and the induced voltage per phase will equal just n phase, number of turns per phase, times E turn. Okay, where n phase is the number of turns per phase. Okay, so like we said last time, E phase, and I'll call it phase A because we're starting with phase A, will equal 2n phi B L R omega m. R omega m is your V, sine omega ET. Okay, guys, and like we said, because we have about the 3-phase machines, so the induced voltage in the next one, which is phase B, will be the same magnitude, 2n phase B L R omega m, but it has 2 pi over 3 phase shift. And E phase C will be the same magnitude again, E and phase B L R omega m, but now it's sine omega ET plus 2 pi over 3 or minus 4 pi over 3, whatever you want. Because, like we said, it is balanced 3-phase winding like said. So I will be having the same magnitude here. So this value is just the same for all of them because that is the magnitude. So we call it E capital V phase, and I will just give it a hat like this. That is the magnitude of it. Okay, and that's what we use to find the RMS value for EMF. So E phase RMS will be equaling, like for any sinusoidal value, the magnitude over square root of 2. That means 2 over square root of 2 n phase B L R omega m, and that's obviously in volts because that is induced voltage. Okay, guys, so that's what we derived last time. So that's how to find out the construction of this kind of a machine and to quantify the induced voltage in the armature of it for each phase. Okay, but there is a very big question we didn't ask ourselves yet. Actually, why it's connected to synchronous, why it's called a synchronous machine, sorry. So for a DC machine, it's called DC machine because it's obvious, because it's typically used DC voltage. So we use DC voltage to push to our armature and everything, so it is a DC machine. Okay, but why are we calling this machine a synchronous machine? Okay, so keep that in mind. It is called synchronous machine because the frequency of the voltage induced in armature is synchronized with the mechanical speed of rotor. Okay, so that is the whole point of this. What I'm saying here is keep this in your mind. NS equals 120 F over P. That is a very, very popular relationship you will be using a lot. Okay, NS for synchronous machine is the mechanical speed of rotor in RPMs. Okay, like we see here, F is the frequency of armature voltage, and P again is the number of poles. Okay, guys, so like I seen here, 120 is just constant. P, number of poles, typically constant. Most of the case we'll be dealing with will be just having a constant number of poles because it's just how you build the machine. Okay, so that means this speed, the synchronous speed, we call this NS, the synchronous speed. Okay, So the change in the synchronous speed directly translated in a change in the frequency, okay? Because 120 over p is just constant, okay? So that's why we call it synchronized. The frequency of the induced voltage in the armature, the voltage in the armature, is just directly related, directly synchronized with the rotor speed, okay? Any change of this will be directly translated and change in that. So that's why we call this a synchronous machine, and that's a very, very important thing to keep in mind. So if you're talking about this machine, like we said, in the generator mode, which is the generator, just the mode we're more concerned whether you're talking about synchronous machine, okay? So the generator mode, to keep that in mind, is just like I just said, the frequency of the generated voltage on stator is synchronized with the rotor speed, and rotor speed for a generator determined mainly by the applied mechanical torque, okay? Because that's a generator, guys, so you know the idea. It's just for a generator we apply an external mechanical torque or force to rotate the rotor to a certain speed, okay? So for a synchronous machine, you know that whatever speed you're applying from outside, it will be directly influence the frequency of the induced voltage in a stator, okay? And that's some sort of a spoiler to keep in mind. It is just, if we're talking about a machine that will be connected to the grid, which is a typical case most of the time, we will be using this to keep its frequency constant fixed at the grid frequency. For North America, it's 60 Hertz. For the rest of the world, most of them, it's 50 Hertz. So for here, that means we will make everything in our hand to keep the frequency of the voltage induced in the stator at 60 Hertz at all time. Otherwise, this generator cannot be kept connected to the grid. Okay, guys? And this, like you're saying here, how do you determine this frequency, or how to just keep it constant? By keeping the rotor speed of the machine constant. Because you know, from this relationship, they are totally synchronized. Any change in the speed of the rotor applied by a mechanical source from outside will be translated in the change in the frequency. And we do not need the frequency to change whatsoever in most of all cases of work. Okay, guys? So keep that in mind for engineering stuff. When you're talking about a synchronous generator connected to the grid to produce energy, to produce electricity to the grid, it is just we will need to keep the speed of the machine constant by any means necessary, and we'll be talking about this in much details later, okay? So that's very interesting thing to keep in mind. You know, if you change the rotor speed, the frequency of the voltage will be changed, and that's not a good thing to do in a public grid, okay? If it's a standalone, that means you're just having a standalone generator like that, a small generator, a standalone generator to just generate to typical loads. You're okay if you are not using frequency sensitive loads also, because it's just all the loads that work with some certain frequency is typically designed to work with the grid frequency also, okay? So if you're just dealing with some sorts of loads that does not affect or not affected by changing frequency, that's okay to keep the frequency change, but it's not the typical case in most of the cases. So in more than, I can't say 95% of the cases you'll be facing, you will be just keeping the speed of the rotation constant to keep the frequency constant at the typical frequency of the grid. Okay, guys, keep that in mind. That's very important, and that's why we call this a synchronous machine. If you're talking about a motor mode, okay, what we mean by a synchronous motor in a synchronous machine, that means that the rotor speed of rotation is synchronized with the frequency of the applied three-phase stator voltage. Because for a motor we are just supplying voltage to the stator, and now the torque will be produced and the machine will start rotating. Okay, for this kind of a machine, whatever the frequency you are supplying the voltage with, because keep in mind again, please, that's an AC machine now, we're not talking about DC machine anymore. So when you're supplying a synchronous motor, because that's an AC machine, you're supplying it with AC voltage, not DC voltage. An AC voltage has a frequency, okay? So you supply the stator of this machine with a three-phase voltage, okay? This three-phase voltage, its frequency will determine the speed of rotation of your rotor. Again, from this relationship, NS will equal 120 F over P. Okay, guys? So whatever frequency of the voltage you're applying to the stator will be directly translated to the speed of rotation of this machine. Keep that in mind. That's very important. Again, I will be just going back to this when we talk about synchronous motors at the very end, but it is the basic formula to keep in mind, okay? So that's why we call this a synchronous machine. Again, because the speed of rotation is directly synchronized with the frequency of the stator voltage, or the armature voltage. Okay, guys? Sounds good. By the way, just as a reminder for you, it is just, this NS is the speed in RPMs, and you can always just transfer between it to the radian per second by just multiplying by 2 pi over 60. So omega s equals 2 pi over 60 ns. So ns is the speed in RPM, while the omega s is the speed in radians per second. So it is just the same, okay? And that means also in this relationship here, omega e equals p over 2 times omega m. That will be the same idea if you just say the speed in RPM, again, ne will equal p over 2 times nm. Okay, so while these omegas are just in radian per seconds, these n's will be in RPM, okay, revolution per minute. So whatever it just means. So don't get confused, because most of the numerical mistakes that happens in the problems to be solved is just in these small minor transformation stuff. So keep that in mind, whatever kind of speed you are using. So most of the time the speed will be given for you on problems and even in the field work by RPM, because it's more convenient to just express the speed like that. But most of our equations are just derived based on the angular speed, which is the radian per second, not RPMs. So keep in mind just this transformation and do not get confused by this. Okay, guys? So again, that is the whole point here. Keep that in mind. Before I'm going, so it is ns, the synchronous speed, omega s, and all that stuff. So for a synchronous machine, okay, omega m equals omega s, okay? We call them the same thing. Omega m is the mechanical speed of your rotor. Omega s is the synchronous speed, okay? So if you're talking about a synchronous machine, you can just deal with them as the same thing. The mechanical speed, omega m, is just the same like omega s, is the same thing, okay, guys? So that's why here I just said that is omega s and that is ns, and I just said for synchronous machine that is the rotor speed, which is the mechanical speed of the rotor, okay? So if you're talking about a synchronous machine, you can call it omega m or you can call it omega s. It is just the same thing. Why I'm saying this, because when I jump to induction machines, I will be just referring back to this, and I will say for induction machines they are not the same. So but for here, for now, just they are the same, so don't bother yourself about now. I'm not trying to confuse you. So for now, in synchronous machine, the omega m, the mechanical speed, is just the same like the synchronous speed. So we are not, so if you can use both of them in your equation and you're solving whatever it is, they are just the same. It doesn't matter, okay? So that hint to be just kept in mind. Okay, guys. Obviously, I can just give you a hint now. I am just saying this, okay, but I will not go in much detail. We'll be referring back to it when you call about induction machine. So if you just trying to have a synchronous motor, and I will be just referring back to synchronous motor after this. So that is the stator of the machine again. That is A dash, okay, and that is here B, and that is the dot, so it's B dash. Actually, that's good enough. I'm sorry. Okay, so I'm gonna say it, yeah, a little bit here. So that is B, and that is the dot, that is B dash, and I'm saying this will be C, and that is C dash. Okay, so that is the three-phase winding and the stator of the machine, like we just explained the last times. Okay, so for a generator, you basically have your rotor is inside here, and this rotor carries the magnetic fields. For just a small machine having two poles, that will be north and south pole like this. So that is the rotor that is carried the magnetic field. Okay, so if it is a generator, you apply external mechanical force to rotate this inside, and like this, these just winding coils in the stator will be just experiencing, will be cut by the magnetic field coming from the rotor, and it's rotating in a speed. So magnetic field, so induced voltage will be just generated in this winding, and you can just collect them outside from the terminals. So each and every one of them has two terminals, so that is the terminals of A. You will be having them here, and you will have terminals for B, so we'll have another two terminals like here, and you have terminals for C like this. Okay, and you know, like any kind of connection in three-phase, we can connect them even a star, Y, or delta, whatever it is, whatever you want to connect them, or whatever the connection is typically designed to be. So that means you will basically having three phases like this. Let me give them the same colors, not to confuse you. So here is the phase A, like a winding. I will have two terminals, and phase B will be another winding. I'll have another terminal, and phase C will also be like that. Okay, so you can connect them whatever you want. If you could just connect one end together, and now you have those three terminals, now it's Y connection. Okay, or you can connect them like delta connection. Okay, that's all happens most of the time outside of the machine. So you get the terminals out, like each winding has two terminals, and then you just connect them in the terminal box of this machine in whatever connection you want. So if you connect one end to the other like this, and now you have those points to connect to the outside world, this will be delta connection. Okay, guys, so that we call the terminals. For a Y connection, this one we call the neutral point. For delta connection, this is your terminals, and you do not have a neutral point. I'm just refreshing your memory about three-phase, but we had a lot of time talking about three-phase connection and that stuff at the very first lectures. Okay, guys? So if you're talking about a generator, you're basically applying external mechanical force on the rotor to rotate it here, and you just collect the voltage that will be appearing around those terminals, each terminals of each phase. Okay, but what about if I want this to be a motor? So I will not apply mechanical rotation to the rotor. We need this to be the result. So rather we just applying three-phase voltage to the stator terminals. So we will just applying three-phase voltages here to the terminals, or here, whatever you're connecting it, like Y or delta. Okay, so you applying voltage from outside. If you're talking about a motor, for a motor mode, we apply three-phase voltage to the stator or the armature three-phase winding. Okay, and let me say it's not just three-phase voltage, but it is balanced three-phase voltages. Okay, and keep this law in your mind. If three-phase balanced voltage applied to balanced three-phase winding, the magnetic field produced will be rotating. Okay, and its speed of rotation is ns, the synchronous speed, 120 f/p. Okay, just for synchronous machine, the rotor mechanical speed nm equals the field speed ns. I know it's a bit of confusion now, but I'll try to simplify it a little bit for now, but I'm not going into deep explanation because I will go back to it and explain it in very much details when I'm talking about induction machines. So simple as that. We just said before, if you have a simple coil like this and you apply a voltage, DC voltage like this to it, a current will be passing in it, and a current moving inside a coil will generate just a magnetic field. Okay, and this magnetic field will be just having a certain north pole and a certain south pole, and it will be just there. Okay guys, so the magnetic field coming from this kind of a DC voltage applied, so that is DC voltage. Okay, so the magnetic field coming from here, B, the magnetic flux density, okay, constant in magnitude and fixed polarity, and you know that. So it will produce a certain amount of magnetic field, and the polarity will keep constant, fixed. The north will remain north and the south will remain south. Okay, but what happens if you made the same, if you just brought a coil and applied an AC voltage to it like this? Okay guys, so that's now an AC voltage. For AC voltage, this current that will be passing here will be changing polarity. Sometimes it will be going like that, and sometimes it's going like that, because that is an AC. Okay, so the current will be also an AC like this. Sometimes it's positive, sometimes it's negative, and it will also change magnitude. So B, the magnetic flux density, will be varying magnitude and also varying polarity. That's why we call it pulsating field. What I mean by pulsating field, it's just like you're saying here. If you have this here, this coil looks like this, so it's an iron core, and the coil is just wound like this, and we apply here the AC voltage, and this current will be just sometimes going inside, sometimes coming from this. So the magnetic field will be also look like a sinusoidal, so B will be looking also sinusoidal. That means its polarity will change. Sometimes you will find a north here and a south there, and sometimes it will change polarity, so it will be south here, north there. not just changing polarity but changing magnitude, because like you've seen here, the magnitude changes with the changes in this sine wave. And that's why we call it pulsating field, because it doesn't hold a value or a polarity. It just keeps pulsating. Okay, guys? But if we just don't have one coil like that, rather than we just have three-phase coils. So if you have three-phase coils like that, so it is three coils connected in a three-phase fashion, okay? And they're just fed from balanced supplies. So you have also three-phase voltage sources, okay? And we just supplying them from it, okay, guys? Like this. Okay, for this, these polarity will not be like that. So if you have the three-phase winding like this, so I have our stator we talked about, and we'll be having the winding like this. So it is A dash, that is the first winding, and that is B dash, and that is C dash, sorry. Okay, so if you apply balanced three-phase voltages applied to balanced three-phase winding, it produces magnetic poles rotating. That means the magnetic poles will be translated from exciting those coils. Will not be just like those guys here, which is a north and a south like this. No, each one of those, so consider at the beginning this will be north, and this will have a south, and then that is north, and that is a south, a north and a south. It will not keep its position like that. Rather, they will just be rotating in a circle like this around the stator. So it will look like pools like this, but it's flying around. How this can be done, I will be explaining this in much details when I'll be talking about induction machines. But trust me for now, okay? If you have this image, if you have just three-phase winding like what we have here in the stator of our synchronous machine, and we supply it from three-phase supply, it will produce magnetic poles, north and south poles like this, but they will not be fixed in position. These poles will be just rotating, okay? Keep that in mind. The coils itself, the coils are fixed. They are not rotate. They are part of the stator, you know, okay? But because of this magical connection, because they are three-phase connected to a three-phase supply, the poles that be resulting from this will be rotating poles. And that's the magic of three-phase winding, okay, guys? So you can get magnetic poles, north and south poles, that are rotating, those produced by fixed coils. How this is be done, again, I will be explaining this in much details when I be talking about induction machines. But please take my word for it for now, okay? This rotating at synchronous speed, we call this speed the synchronous speed, ns, which equals 120 f over p. Okay, guys? For the synchronous machine, the mechanical speed of rotation will equal this synchronous speed. So the rotor will be rotating at the same speed of the magnetic poles, like I said here. So if three-phase balanced voltage applied to balanced three-phase winding, the magnetic field produced will be rotating, and its speed of rotation will be the synchronous speed 120 f over p. And just for synchronous machine, the rotor mechanical speed nm equals this field speed ns. And that's why we call it a synchronous machine, guys. Okay? I hope this understandable, does not confuse you. Okay? So I just took you here to just find if we have a coil and different kind of excitation. If you just apply a DC voltage like this, it will produce you a certain north and a certain south, and they will not just go anywhere because that's a DC voltage. That means the DC voltage, it's a constant magnitude and a constant polarity. It's either positive or negative and does not change polarity or change magnitude with time. Okay, but if you just get an AC voltage like this, you know that the AC voltage changing magnitude and changing polarity with time. That means the magnetic poles, the north and south pole, that will be just resulted from this current, AC current going into the coil, will be pulsating. That means it will be changing magnitude and changing polarity. So the strength of this magnetic field will be changing with time, and its polarity will also be changing. Sometimes it will be a north, sometimes it will be a south. Okay, that we call a pulsating field. But we don't just have one coil, rather we have three-phase winding, three-phase coils connected together like this in Y or in delta, whatever it is. Okay, and supplies from three-phase supply. Magically, those is not pulsating anymore. It will be have poles like that, but rotating around the circumference of the stator. Okay, how this is done, I will prove it to you, but not now. Just take my word for it now. Okay, so from this connection, you will be having a rotating magnetic field, poles that's rotating around the stator at a speed we call it the synchronous speed, ns, 120 f/p. And for a synchronous machine, because of how this machine works, I'll be just referring back to this when I'm talking about synchronous motors. The rotor of the machine rotates at the same speed of this rotating speed of the stator field, not the stator body, because the stator body, the stator coils, they are stationary in position, but the magnetic field produced by them, the poles produced by them, is rotating around the stator circumference. Okay, in a speed we call it the synchronous speed, and it equals 120 f/p. So that's why I told you, for a synchronous machine, the mechanical speed equals the synchronous speed, because that's how this machine works. But when I jump to talk about induction machines later, they will not be the same. The mechanical speed of the rotor will be different from the synchronous speed, which is the speed of the magnetic field of the stator. Okay, guys, please don't be confused about this. The stator itself is fixed, its speed is 0, it does not rotate. But the magnetic field of the stator is rotating. The poles, the magnetic poles generated by the stator is rotating by the synchronous speed. Okay, that is how it works if you just get a three-phase winding excited from a three-phase supply and both of them are just balanced. Okay, how this works actually physically we'll be explaining in much details when I talk about induction machines, but for now keep that in mind. Okay, so the stator itself is not rotating, but its field is rotating, and the rotor obviously rotates because that's a rotor, but the speed of the rotor will be the same like the speed of the field of a stator. Okay, so the mechanical speed of the rotor, Nm, equals the synchronous speed, which is the speed of the rotating field of the stator. Why? Because in a synchronous machine, the stator winding are three-phase winding connected to a three-phase supply, and that's why we just have something like that. Okay, guys, I hope you understand this. Okay, so again, just take it for granted for now, and I will be just talking about this, how this actually works, and how just from a fixed positioned coils, if you just make them three-phase connected to a three-phase voltage supply, you will be magically having a magnetic field that's rotating. We'll just deriving this step by step like we just did before, but we'll be doing this in induction machines because it's more convenient to talk about it there. Okay, but for now, keep that in mind. Okay. Okay. So again, to just make this very clear, the Nm for synchronous machine, so for a synchronous machine, Nm equals Ns. Nm is the rotor mechanical speed, and ns is the speed of magnetic field of stator, not the stator itself, the magnetic field of stator, okay? And this will be equaling 120 f over p, and that's why we call it a synchronous speed, okay? And you know that's for any kind, so those n's are in RPMs, but you can just multiply both of them by 2 pi over 60, and now you'll be lined out with omega m. So omega m equals 2 pi over 60 times nm, okay? And by the same meaning, omega s will be equaling 2 pi over 60 times ns. But you know, again, for this, for synchronous machine, omega m will be equaling omega s. Okay, guys? Both of those are mechanical speeds. So both of those are mechanical speeds. So the speed of magnetic field, again, that is the mechanical speed of magnetic field. So both of those are just mechanical speeds. That's a mechanical speed and that's a mechanical speed. Okay? But what about the frequency of the induced voltage? Like we said before. Okay? So omega E, the electrical speed like this, equals P over 2 times the mechanical speed, which here for synchronous machine, it equals the synchronous speed. Okay? So omega E equals P over 2 omega S. Okay, guys? Or omega M, whatever you want to just call it. Okay, guys? That is the omega E, and omega E is the electrical speed. Okay? What does I mean by this? So, to understand what I mean by electric speed is basically omega E, which equals 2 pi f. The frequency, you know, for any induced voltage. Okay? That is mean that is representing the frequency of induced voltage and stator. Okay, guys? So again, for synchronous speed, omega E equals, for anything actually, omega equals 2 pi f, but you can also calculate it by multiplying P over 2 with the mechanical speed, which is here for synchronous speed at this synchronous speed. Okay, guys? So actually you can derive this relationship, you know from anything that's omega equals 2 pi f, yeah? It's a very well-known relationship. Yeah? So actually it can be derived from here. You know that omega E equals P over 2 times omega S for a synchronous machine, yes? That means P over 2, omega S will be equaling what? 2 pi over 60 times ns, yes? So it's P over 2 times 2 pi over 60, ns equals 120 f over p. Okay, guys? So 2 multiplied by 60 is 120, goes as it's 120, and p in the numerator goes with t in the denominator, that is equals 2 pi f. Okay, guys? So they are all related to each other. And that's why we said that it is just like I said. So omega E equals P over 2 times the mechanical speed, and it's also equals 2 pi f. And that's why I'm saying for this kind of a machine, the mechanical speed is just synchronized with the frequency. Okay, so omega E, which is the electrical speed, can be just calculated from 2 pi f, and also from saying that is equal P over 2 times omega m. Okay, and that's why frequency is synchronized with the mechanical speed. Okay, guys, that's why we call it synchronous machine. Yeah. So I took a little bit of time here trying to just make these things obvious in your mind. I know it's a little bit confusing, so take some time to revise this well, okay, and take some time to try to understand this when I talked about the different forms of magnetic field coming from different excitation, if it is DC voltage or AC voltage, single phase AC voltage, so it is just a single phase, one phase AC voltage, or it is a three phase AC voltage. Okay, so that is the thing we'll be using here, the three phase AC voltage, balanced three phase voltage applied to a balanced three phase winding, because that's produces a rotating magnetic field. Poles, magnetic poles, that's rotating around the circumference of the stator, even if the coil itself is not rotating. Okay, the rotation of these poles comes in a speed. This speed we call it the synchronous speed, 120 F over P. And it's something unique for the synchronous speed, that the mechanical speed of the rotor is just equals the same speed like this, and that's why we call it synchronous machine. In induction machine, it doesn't work like that. The mechanical speed of the rotor does not equal the synchronous speed, and that's why we didn't call it either a synchronous speed. It's something else. Okay, guys? Keep that in mind. That's very important to understand this. I will be just hitting back on this at the end of explaining the synchronous machine when I talk a little bit about the synchronous motor. So I will be referring back to this, and I will just explain how actually the synchronous motor works. And we will be just given a huge time to explain this in much details when we're talking about induction machines. Okay, guys? Okay, I hope you are just in line with me. Next time we'll be talking about the modeling of synchronous machine. We'll be just deriving the equivalent circuit model of it like we did before in DC machine, and just understand how to use it to predict the performance of this kind of machines. Okay, so thanks so much for joining me today, and I hope to see you next time.